Was sent out earlier this week. Harvey says you can't hear me, so I'll come stand over here a little bit closer to you all. It's a product of the University of Leiden for all of his degrees. He had a brief foray across the channel to Cambridge, England, but then he was back to Leiden very quickly. He's now a professor and director of the observatory there. His research interests, as you can see, well, you'll see on the second slide, all the different things that LOFAR can do and the full survey power. But his research interests focus on large-scale structure, active galactic nuclei. Essentially, he's a perfect match for the high-energy division, and we'd love to adopt him. He's a master of multi-wavelength astronomy. If you look at his webpage, you'll see essentially all the big telescopes of the world that he's observed with. He's both a member of the founding group for LOFAR telescope, and he's also the leader of, I think, mostly what he's going to spend his time on the LOFAR survey. And right now, his student gave me some of the amusing facts about LOFAR. I'll just go through a few of them before I actually turn this over to Huub. But there are 50 stations from Netherlands across Europe. It's a digital software telescope, so you can simultaneously observe multiple pointings on the sky. Any number of pointings only limited by computational resources. A typical 8-hour observation gives you a tenth of a petabyte of raw data. And one of the things that amused me was LOFAR is actually a time machine. You can look back about 5 seconds in time by storing the actual raw voltages from the antennas. I don't know if you're actually going to mention any of that, but that's an amusing note. The survey that he will eventually complete is going to be 3,500 pointings, 16 terabytes of data per each individual pointing, 100 million sources, 100 times more than NDSS, order of magnitude 50 times deeper than NDSS for typical spectral index, order of magnitude better resolution. Anyway, with that advertisement, I hope you're going to tell us wonderful things, and I give you the floor.
Well, thanks for coming over. Ooh, that's... I was going to say thanks for coming and having a sandwich with me, but I can't see that now anymore. Good. I'm going to talk about LOFAR, the telescope, and its science. And it's to some extent always unfair that an individual talks about such a huge instrument. We're just doing the sums. We in Holland are with 70 million people. So here you are with of the order of 300 million. I mean, LOFAR was of the order of 150 million. So if you kind of look into that per capita, I mean, that would mean here the equivalent of a 2 billion euro project. So in that sense, it's really visible in Holland, and we're really proud of it. This is basically the part of the machine. What you see here is a station. This is the station in England, near Chilbolton, run by Oxford. And two systems here. There's the low band antenna, which you see here, and the high band antenna, which you see there. If you look at the low band antenna, that's what you can see here. And if you look at it, so there are copper wires here, there's a ground plane here, and what you basically hear is a kind of a low noise amplifier, and then a coax cable goes through the a cabin somewhere. Then here's a tiny fraction of the high band antenna. That's what you're seeing here. This is one tile. There's 16 by 16 antennas here, packed in plastic. And this together, I mean, there are 96 of them. And the big thing with LOFAR is then, if you basically phase up those antennas, you simulate a telescope with a diameter of 50, 60 meters. On the one hand, that's very unhandy, because you're basically not really tracking sources. You've got all kinds of nasty side lobes. On the other hand, it's cheap. You don't need an expensive dish, so you can build many of them. Another big thing is that, if you look at those dipoles, well, you think they're standing there. But the big thing is, of course, all the data stuff. What you see here is there's a box of computers, electronics, and they basically do the beamforming on the sky. So there's two systems. This is the low band, which runs from maybe 10, 15 megahertz up to 90 megahertz, and the high band runs from 110 megahertz up to 40 megahertz. And this is the big trick. Beam combining is done there, and that basically gives you beams on the sky. you can observe now at the bandwidth of 96 megahertz, but we can also observe it two beams of 48 megahertz, or 4 beams of, well, you do the sums. So that's beautiful. This is one station. If you look at the core of LOFAR, I mean, in 2008 or something like that, land was acquired, and then slowly building went on. And this is kind of is now. I mean, there are a number of stations, 6 of them in total, and with each station split into 2. And here is the low band, and here the high band again. If you look at the Dutch array, I mean, in the core, I mean, this baselines up to 3 kilometers, there are 24. And then in the northern part of Holland, there are of the order of 60 more stations, remote stations. So here's Amsterdam, here's Leiden. If you want to visit us, there's a big airport, Schiphol, in the middle of it. And if you take the train here, I mean, you basically, it takes 2 hours to get to here, and then you have to continue with the car. And the great thing about LOFAR is, to some extent, it's in Holland, but it's also in Europe. And what's interesting is that for, say, €1 million or dollars, you can buy yourself your own LOFAR station. And that's really what has been happening the last 5 years. So there's that station in England. There's a station in France. There are 6 stations now in Germany. There are 3 stations now being built in Poland, and there's also now funding for station Ireland, and the Italians keep promising us that they're also going to find money for it. So the science, what I really like LOFAR, it's really multi-purpose, and so we're working on all those different science topics. Personally, I'm kind of PI of the LOFAR survey, so I'll spend all my time on this, but I'll say a few things on the other things. I think that LOFAR, especially if you look at the high band antennas and the layout there, is basically an EOR machine. And EOR is being observed at a number of fields, and the amount of data is now collected is pretty staggering. I think something like 2,000 hours in total. And the big challenge for them is to properly reduce that data. And that's really hard. And I'll show later how hard it is and why it's so hard. And I think that at the moment they have the best constraints ever on the 21 centimeter fluctuations around the epoch of reionization. But what you really want is a detection, and that's clearly not there. I mean, they need to go down another factor 2 or 3 or so before they really start testing realistic models. I think they've excluded now a few models that no one believed, and yeah, that's progress, but still. The other thing I'm not going to talk about, but there's a recent Nature paper there, is that LOFAR turns out to be also an excellent cosmic ray machine. And what basically happens is that when a cosmic ray kind of enters the atmosphere, then you get a cosmic ray shower of charged particles, protons, electrons, muons, and they basically give blips on the antennas. But basically what you see is a slab of radiation comes in, and then the timing of the antennas is really accurate, so we can basically see such a slab coming in, so blip, 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 blip over the array. And those are actually measurements, something coming in. You basically see here the time delay of the signal coming in. And what is pretty amazing is that you can indeed detect cosmic rays, you can get an idea of direction, you can get an idea of the power coming in, and then also you can get an idea of how many electrovolts you were looking at. So that's really progress. And also from the shapes of detection, you can even start getting what kind of cosmic ray came in. Was it an iron particle, or was it something else? So that's a really nice technique. So transients, I mean, because of the big beams, LOFAR is indeed a beautiful transient machine. They have a few very nice detections. Magnetism, sun and space weather, I'll say something a little bit later. So now what I'll do is now I give a fairly random collection of interesting results. without explaining all the physics and astronomy in detail. And then I'll discuss data reduction of deep LoFAR data in some detail, and then I'll go into some results, especially focused on clusters. This is nice in the sense that what we never kind of was in the science case originally, but we can do radio recombination lines. And if you here look at a carbon atom, and then if you have an electron going around it, an electron is a really high orbit. Think of n is 450, 451, 455. Then that system you can get recombination lines, and that probes kind of cold gas, fairly diffuse, a little bit similar to what people see with the H1. And we're very, very happy that after a lot of work, a student of mine, Leo Morabito, could show that you could do this at 150 megahertz and really start detecting in absorption carbon recombination lines. And that's cool, because if you can do it against M82, we should be able to do it against any of the strong radio sources, all sky. The radio sources that are very strong, I mean, many Janskis are redshift 3 and 4, and those would be good candidates for this as well. What is nice, you can also observe the sun. And what is cool is that, like here, although there is a big event next, but it's in August 2017, but you really want to see the solar eclipse. And that's kind of hard in Holland, because we had a solar eclipse March last year, and it's fairly clouded. And this is kind of one of the best pictures of the solar eclipse, so that was a bit disappointing. But yeah, if you've got a radio telescope, you can also look at it. And this was the solar eclipse in radio. So that was, that was kind of cool. The other big challenge, and you see a little bit later there, is so we have that international array with those enormous baselines, 1,000, 1,500 kilometers. So in principle, you should be able to make images at 50, 60 megahertz of resolutions of better than an arcsecond, which would be an enormous step forward, because I mean the state of the art kind of this field was 5 arc minutes, and that's an enormous step forward. And after a lot of work, Lea Morabito, a PhD student of mine, this is the first decent image at 50 megahertz of a high redshift radio galaxy. And high redshift radio galaxies are kind of like quasars that are associated not with a quasar, but with a very massive galaxy. They often have lots of CO, dust, enormous Lyman alpha halos, and we like to understand them. And what you see here is kind of like one of the very first images at 50-ish megahertz with such a very nice spatial resolution. This is in HBA, so the 150 megahertz, where Varenius looked at M82, and because with the same baselines, but the frequency is higher, the resolution goes up, and this is basically all the supernova remnants in M82. So that's a very nice result. Paper is out. Something else you can do, and this is, you can look at parts of the galaxy and look at polarization structure. And the data what you see here is basically shows how the magnetic field is entangled, and the magnetic field we think comes from our local environment. It's a beautiful way of probing the magnetic field of a galaxy. Good. Those are kind of some random results to also to show that the machine is clearly working. And so when we started LoFAR, there were a number of key projects, and one of which was to survey a large fraction of the sky. And well, why do you want to do that? Well, in principle, if you do that, you get, I mean, given the capacity of LoFAR, given a few years of observing, you should be able to get something like 30 million sources. You get basically all the AGNs in the sky. you get half of them will be, roughly half of them will be starburst galaxies. You'll get 100,000 clusters where a good fraction have shoot radio emission. You can hunt for really rare sources, for example, redshift 7 radio galaxies. People have done some studies for cosmology. There are interesting things you can do. You get a complete view of the galaxy. So we had a big team and a big project, and we basically made a good plan. We wanted to detect high redshift radio galaxies, and George Miley is leading that. We had the goal of trying to get of the order of 100 beyond redshift 6. Star-forming galaxies, if you go really deep with LOFAR, and we kind of know we can do that, then we'd like to go deep enough we get good samples of star-forming galaxies beyond redshift 2, and then study voids, but also overdensities, and really the extreme overdensities should be progenitors of nearby massive clusters. Then a number of people here are working on that, on clusters and relics, halos, non-thermal emission, and we kind of set the survey goal so that we would extend those studies up to redshift maybe half or 1. At the moment we've got beautiful examples, and I show a few in my talk of 0.1, 0.2 clusters. We'd like to really push this forward. And then there's a whole list of other stuff you can do, studying AGNs at low and high redshift, aspects of lensing, nearby galaxies, etc., etc. So the plan we came up with is this plan. So this is flux limit. It's 5 sigma versus frequency, and this is basically the low band. So all sky and deeper tiers, and this is the HBA survey. So aiming at RMS levels of 100 microjensky, and really deep levels of maybe 10 or 20 microjensky. And what you see here is that if you compare that to the old generation of surveys, I mean, we're doing so much better, just almost unbelievable. And yeah, this is basically the EMU and the new Westerbork surveys that should attain noise levels at 1400 megahertz of 1020 megahertz, microjensky, and this is the interesting VLA survey. Good. How do we make images? So the first thing is that we've got lots of extremely high quality data. So amplitude and phases versus time, and the quality of the data is more than excellent. And in that sense, it should be kind of easy to make images. However, if you look at the challenges, there's a big list here. I mean, the first thing is the data rates are just staggering. I think if you think about each station has a connection of 10 gigabits per second to the central correlator. And then if you correlate that, you basically, the output of the correlator is, I think, half a terabit per second or so, but something input in the correlator is terabit per second, so that's really staggering. And then we need to deal with radio interference, which is not such a pain, in the sense that we're really worried about that, because why the hell would you put a radio telescope in Europe? And to some extent it's a compromise between those two things, in the sense that we really need to make use of fiber networking, but all the fibers are already there, so we don't really have to pay for it. And if you have to do all the fiber networking on an empty plane, I remember the early days when Rick Purley, your discussion with him whether we should put LOFA there, and he was telling me, shit man, you need to talk to all those farmers and say, look, you have to put those fiber networks there, and that will cost you a fortune. So radio interference is important, but we can, in HBA, deal with that, and also a significant fraction of LBA deal with that. And the reason is that we sample at high bit rate, high time resolution, high frequency resolution, and that allows us to identify RFI. There's something of removal A-team sources. And the idea is that there are sources on the sky that are really bright. Cygnus A, Taurus A, Cassiopeia A, and they're really bright. 10,000, 50,000 Jenskys. But we wanted to go to those millijensky level, of microjansky level. And which is handy because you have that those dipoles, and that gives shitty beams. So anytime one of those things come into your side lobe, they completely dominate the signal, which is not handy. And you really need to deal with that, and that I think holds us up for 2 years or so, something like that. Timing of the clocks. Our clocks are not good. The central clocks are okay, but if you go to the outer stations, they're not on one clock, so we need to solve for that. That's a pain, and we know now how to do that, but it also took some time. And then the big thing is the ionosphere. That's this thing here. I think that's a layer, a few hundred kilometers, and it basically does the same thing to radio sources what our twinkling atmosphere does to stars. So they kind of move up and down. And if you look at the mathematics of all that, it's kind of like the same formalism. You need to really understand that. And I'll show you the big problem. This is an image that Huub made of a famous cluster, 2256. And this is a GMT observation. Field of view, I think it's 2.5 or 3 arc minutes. And you have a source here and a source here. And you made an image every minute. And you see the thing dancing up and down. That's an absolute nightmare. Or this is show the same idea. Nightmare 2. So what you see here is LOFO observations, and using only the Dutch array, and making only images of a resolution of 3 arc minutes. Yeah? If the ionosphere is kind of quiet, that's what you see. And if the ionosphere is angry, yeah, then this is what you see. And the problem is not basically shift and add. It's basically the ionosphere is kind of decorrelated from here to there. The ionosphere almost decorrelates in patches on the atmosphere of 10, 20 kilometers, corresponding to, I don't know, 10, 20 arc minutes, all depending a little bit of frequency. So you have a big problem there. And you basically, I wouldn't say you need to reinvent radio astronomy, but kind of. So Reinhard here did great work there. Wendy Williams, a student of mine, and Tim Shimwell and many others worked on this for 5 years to basically build a multi-conjugate adaptive optic software machine to be able to deal with this. And the basic idea Reinhard and others came up with is the following. Here you see a LOFO field of view. This is the moon here. Basically because I was giving a similar talk in Pasadena a year and a half ago about surveys, and the unit of importance is always the moon. If you can map the moon in one go, you're kind of like, could go to the conference. And if you could map a significant fraction of the moon, you really kind of were the hero there. And so this is the moon, this is the LOFO field of view. So the moon is 30 arc minutes, LOFO field of view is say at 150 megahertz, 4 by 4 degrees. And then the big trick is here, you pick out all the bright sources here, brighter than say half a Jansky, and then you make up some kind of triangulation scheme, here, you boundary here, and then you try to calibrate all those patches in an independent way. And because you're dealing with radio data, that's annoying, because you think of visibility. Visibility, that's the thing you measure, and the single visibility is basically the sample of a Fourier transform of the entire sky. So what you basically then have to do is you take a patch with bright sources, and then you basically need to remove all the other sources from your data, find out the correction for that patch, and then iterate and iterate. So that's the whole scheme is really elaborate, partly because of this problem. You have to go all the time back from the UV plane to the image plane, and also partly because it's very intense, compute intense. So every time you kind of can average the data, you should do it, but not too much, because then you lose, for example, spatial resolution. And in the paper that right now it's here, but you basically, if you don't do this kind of AO correction, but basically do one correction for an entire field, I mean, you're not happy. No? And then if you basically then iterate 5 times, where you simultaneously try to understand the beam and the ionosphere and take that into account in the imaging, and basically it's getting fairly perfect. So back to the moon again. If you now look at, and this is new part of the PhD of Wendy Williams, this is the moon again, and then if you look at here the image, it's only 8 hours of data. Noise levels are of the order of 100 microjansky. The scale what you see here is 4 × 4 degrees, and the spatial resolution is 5 arcseconds. And that's why you see with this thing is this thing. This thing is this thing. So, you were asking, every image has something weird, and you don't understand this thing here. Yeah, it's close to a group, but we don't really know why it's there. And so, yeah, just for fun, this one is this one, and this one. And this is random snapshots from this 8-hour data set. It's good that the lights are off now. Yeah, so this is very cool. I really enjoy showing this. So this is the Bootes field, which is a famous field if you want to do extragalactic astronomy, because NOAO started working on this field. They spent, I think, 100 or 200 nights of 4-meter time. There's X-ray data, etc., etc. And this is basically, so this is something you get for free, in the sense that of the order of a bit more than 3,000 sources of the 5,500 sources that you get in one 8-hour observation. Of those 3,300 sources, you can identify 70% of them, and then this combination of photometric redshift, but also lots of spectroscopic redshift, and what you see here is radio power versus redshift, which is rather cool. So we can write lots of papers on this. And what you can do in this data set is look which one are the AGN and which ones are the starburst galaxies. And from that you can look, for example, at the evolution of the famous radio infrared correlation, just from one 8-hour data set. So here's the evolution, and what we're finding at the moment is similar to what other people are finding, is that the ratios go down a little bit, and with something like 1 + c to the 0.3. And what we're exploiting this for is that we have now the combination of LOFAR data and Herschel data, and you can turn that around and then say, look, so we have you take 100 of those LOFAR pointings. Herschel has surveyed something like 1,500 square degrees in the northern sky, and then you've got radio data, you've got Herschel data, and that combined you can try to use to make a radio infrared photometric redshift. Yep. And if you do that, you can, for all those radio sources with the Herschel detection, you can estimate the redshift. Not very accurate, 0.2, 0.3 or so, but you can do that for the up to redshift 2.5 or 3. And if you then combine that, all those redshifts, you can look for clusters and also protoclusters in the early universe. And this is one of the examples we're now studying, where this is in the Bootes field. So here we basically know where the overdensities were, and then what you see in contours from this technique where the radio/Herschel overdensity is. And this is just a nice candidate at redshift 2.8. So we are at the moment trying to exploit this technique in a massive way and to get really nice samples of the progenitors of normal clusters between redshift 2 and 3. Another holy grail is getting redshift beyond 6 radio loud quasars. And for a number of reasons that's a fairly holy grail. I say the most important reason is that if you find a few, you can do spectroscopy with LOFAR, 21 centimeter spectroscopy. And then the idea is you basically can start studies like the Lyman alpha forest, but then the 21 centimeter forest. And let me say, and in the Buddhist field, we're very happy that we have a detection of a quasar at redshift 6.2. So it's a big relief for us because no one could promise us that those bees would be there. And they are there. So there's only one in one field. And then the idea is that, and this is simulation for an SKA, LOFAR can't do this, because this source is not bright enough. But the whole idea is that ultimately we basically would make spectra here, where the idea is that the universe was first not ionized and here partly ionized. And then with those kind of spectra you can study how ionization would proceed, which is really nicely complementary for the 21 centimeter fluctuations, because what you there do is try to do this on scales of many arc minutes, where we can do this now on a scale of a few arc seconds. So it would be great. Okay, something on clusters. This is some of the simulations that Reinhard made some time ago. And as you know, you all know what clusters of galaxies are. You all know that they have X-rays, and if you collide them, you basically get traveling outward shocks. And here is a shock here, and the whole idea is that if you have such a shock with a Mach number of a few, you have a bit of magnetic field, you get lots of radio emission. And there are very famous examples there that kind of learn us a lot about how those merging clusters work, about the magnetic field, particle acceleration, etc. And one of our very famous examples is the sausage cluster. You must have seen this one. And there it is, the sausage cluster. And I had a student that started with me 2 years ago, Dewey Hao Zhang. He was ambitious, came from Vietnam, and I said, well, let's give him the LOFAR data for this cluster. And you see here all the problems here. There's Cassiopeia A here, 8 degrees away. Cygnus A is also is 20 degrees away. And it's to his credit that he didn't give up on this. It took him 1.5 years to get rid of all the RFI, all the ionosphere. This source, I don't know, is so much brighter than, you probably know how much brighter is than the social cluster, Reinhard? 20,000 times. So this was just, but here's the result. Again, such an enormous field of view. Again, noise levels, despite all those problems of the order of 100 microjensky. And again, as a bonus, you get all the other stuff around it. And if you then zoom in, this is the absolutely gorgeous LOFAR image. And what you see is the X-rays. What you see here is a number of head-tail galaxies. And here, the beautiful shock. Okay, I explained this. This is the idea. And if you now look at the image, it's pretty impressive in what kind of detail you see this shock. That's a shock of 2 megaparsecs, Mach number is around 4, and here the head tails there. I mean, we call it a sausage cluster. I don't know, because it looks like a sausage. And the rumors that we used it, named the sausage cluster, we were working with Marcus Bruggen and Matthias Heuft, who were coming from Germany, is not correct. And the thing is that we now can make beautiful spectral index maps. And you might have seen a few before, This is the one from LoFAR data, with a resolution of 5-6 arcseconds, combined with GMRT data. Yeah, that's at 610 megahertz and has a resolution of 5-6 arcseconds. And what you see here is that, at the front of the shock, the speckle index is fairly flat. I think of 0.6, 0.7. At the back of the shock, that's the blue stuff there, it goes down to speckle index of -2. You also see is that there are lots of other shocked areas. If you look at the southern part, you can basically see that the shock is much more complicated. I think we kind of understand the northern part, and the southern part we're basically working on this. I kind of like to show this image from Reinhardt's thesis. It basically shows that with some relatively simple hydro simulations you can get a number of parameters for those clusters you basically can't get in any other way. And one way of looking at it, I'm not sure that it's, so you've got two clusters merging, and you've got a northern and a southern pancake emerging from there. And if you look at this pancake, then you can play with the parameters of the cluster, mass ratios, impact parameter, and viewing angle and all that. And from the simulations, it's really clear that you need to be able to see the system located in the plane of the sky. Mass ratios 1:1 is not going to work, because then you would have a symmetric system. 4:1 is not going to work because you basically wouldn't get much of a shocked southern system. So 1:2, okay-ish. Impact parameter needs to be smallish, so it needs to bang head on. And if it's just a significant impact parameter, you basically get some swirling pattern. It doesn't really work. And the time since core passage was estimated of the order of a gigayear. And Julius Donnert just submitted a fairly sizable paper to come up with estimates for many of the properties of this relic, combining lots of radio data, X-ray data, etc. And so you can see you could get all kinds of properties of the shocks, indication of magnetic fields, etc., etc. So it's beautiful what you can get out of this. And so it seems that with systems like this we can learn a lot about clusters. And the question I ask myself, okay, is this scenario completely correct, or are we missing stuff? I don't know. I'll now show you a number of puzzles. And some of those puzzles we haven't solved yet, but it's kind of nice to end with that. So one of the puzzles is, so if your shock is a pancake, yeah, then it's clear what, to some extent, the brightest distribution should be. It should be some kind of parabol. That's what you see here. Yeah, and this comes from various simulations. See that, and what you see in practice is that the observations here, a flat brightest distribution, and then it goes down. I don't think we understand why. The other thing we try to do, and we really need to improve on the LoFAR image because it's one single band many years ago. But we basically had the silly idea of also looking at those sausages at high frequency. So 16 gigahertz and 30 gigahertz. That's what you're seeing here. And this is the overall spectrum, integrated spectrum, where you could plot total flux versus frequency, and those are the points here. And the big problem there is that if you look at simple acceleration models, you would really expect this to be a power law. And basically, you've got particles going into diffuse shock acceleration going through the shock, and you need to get a power law out of that. If not, to some extent, all hell breaks loose, because it's easy not to get a power law, but you basically need to start fiddling, for example, with the magnetic field. That's unevenly distributed over the shock, or you need to, for example, fiddle with particle acceleration, where you might say there's some residual particle acceleration in the wake of the shock, etc., etc. I don't think we really know this, but this is clearly an important constraint. The other riddle comes from weak lensing. Will Dawson and James G have done wonderful work there. And this is one of the weak lensing maps. And with weak lensing, the beautiful thing you can do is, of course, determine masses for the subclusters. And the best guess is that the masses are equal. Fine. But if the masses are equal, why would you get a big shock in the north and a small shock in the south? And that's what comes out of the lensing. I think it's fair to say that the lensing 2-to-1 is kind of still permitted given the error bars, but it's still a bit of a puzzle. The other thing is, and this is work by Reinhardt that he recently submitted. This is again a beautiful big image. What you see here is a non-shock of this cluster, and where you see the same specular index structure. So flat in the front means flat specular index, so you expect shocks happening there, and due to particle losses you basically see things getting blue, which means that the high frequency part loses energy. We call this the toothbrush cluster. Yeah, it's and I think that this is a montage of all the data. So what you see here is the specular index map. What you see here in white contours is one of the radio images. What you see here is the X-ray. And what I'm not sure we understand is how do you get such a shock? And the idea is that you basically have two clusters here, one here and here. They kind of collide, you get an output shock, but why the hell is this thing sticking out? Yeah, it sticks out. So we're working on this with Reinhardt and Marcus a few years ago, and Marcus came up with the silly idea. So you take two big clusters and you take this sneaky one, and you have that sneaky one merge, but you make sure you have got a 2-1 and you shoot it from the back, so you don't see it. That's always good because you can't. And then you let it develop, and then if you look at the image, and then here where you feel that this non-shock should be, and when the energy is dissipated, then I think you get something that is that's clearly there and might be working, but I don't think we really have found kind of observational evidence that this is really happening. So I think it's a nice working hypothesis, but I'm not sure we're there yet. So I think the basic scenario kind of needs to be correct. You need to have merging clusters, and because there's clearly a lot of evidence that there's a connection between those relics, halos, and the merging of clusters. But in detail, I'm not sure we understand this. I don't think projection effects can solve some of the riddles there. I think minor merges certainly plays a role, because you see, especially in the deeper lower images where you have multiple shock systems, so merge emission needs to play a role. This magnetic field generation within the shock, difficult to prove, but it's clear if you look at the polarization, for example. I mean, compression of magnetic field needs to some of the source being highly polarized, so that's certainly happening. A big thing is that if you want to accelerate particles from the thermal pool, just from the X-ray gas, there's a consensus you have an efficiency problem. I mean, you need to, can you get enough radio out of such a shock? And the answer is that's hard. What some people are proposing is that you basically accelerate particles not from the thermal pool, but from the non-thermal pool. where the idea is that you have had a previous generation of, say, AGN that stopped being active, and some of that plasma still exists there, and on top of the thermal gas, and it's basically that you accelerate that to high enough energy to get the radio fine. My last slide before the conclusion. This to show is that we're working on a number of clusters. This is a paper that Tim Shimwell just submitted, and he's done a really nice job in reducing the data, and there's lots of stuff in this cluster we don't understand yet. So what you see here in red is the LOFAR image, which is reproduced here, and in blue is the X-ray. And so if you look at this, there are a few mysteries in this image. First of all, I didn't talk about halos. Halos are diffuse emissions, not kind of like directly associated with those traveling outward shocks, but basically they follow the X-ray emission. And there are a number of models on how people try to produce that, either by proton collisions, where you basically have relativistic protons in your X-ray gas, and collisions will give electrons, relativistic electrons, and that might give the halos. And, but there are problems with that model. For example, we don't really see a lot of gamma ray emission from clusters, and that makes this model difficult. Yeah, our good friend Gianfranco spent the last 10 years, I think, to look at turbulent reacceleration, and I think kind of like he might even be correct in the sense that there's a reasonable match with the observations. But there's a hole there. Yeah. I'm not I mean, I'm sure that Gianfranco has an explanation for that, but there's still a hole there. And if you think of a turbulent cluster due to a merger, then why wouldn't we have any turbulent stuff there? Then there's this thingy here. It's not really an AGN. It's very steep. It's, what is it? I think 3.5 megaparsecs away from this cluster. And we don't know what it is doing there. And then there's lots here, which is probably a combination of AGN that are being mixed up with the merger, and a few spots here that I guess will be kind of weak shocks. So again, this is only an 8-hour data set, but my suggestion is if you look at any cluster, you go deep enough, you can really see the entire shock structure. So I've talked for 50 minutes, which is enough for a colloquium, and this is my conclusion. Thank you.
Turn the lights on and break everything up.
Hi there.
Any questions for our speaker?
You mentioned the survey. When will the data become public?
I think we've done now of the order of 10% with Northern Sky, a little bit less. We have a first draft of a paper describing all the data we've taken in the headaches field. We hope to kind of submit that maybe this summer. And making really public the whole thing will take another 5 or 6 years. So in the meantime, we are collaborating with people if they want to work with us on small bits and pieces here and there.
You showed a map of the electric magnetic field, the Havercorn result. So the dominant systematic in that must be the side lobes and the ionospheric variation, Or what's the dominant systematic in that? How do you get down to those surface brightnesses when you have large contaminating sources off axis, large polarized contaminating sources off axis?
I don't think we have. I mean, most sources are unpolarized at those frequencies, so I'm not sure that that's.
So what's the dominant systematic in the map?
I think the ionosphere there.
So that was my question.
Yeah. We haven't done any. So the next step here is so that fast calibration has really improved things, but we haven't only done that for continuum images and not yet for polarized images. So that's something that a few people are now working on.
Do you have a transient alert system to what you see transients?
So the few transients have been discovered long after the fact, and so for various reasons the whole transient detection is much later than we all had hoped for. But one of the things that is working now is there was a project to basically cross-correlate all the dipoles in the core and to make an image every, I don't know, 10, 20, 30 seconds of the sky. And that's at very low resolution. That's now kind of working, which is really cool. Yeah. But yeah.
Are you running high band and low band observations simultaneously?
No.
Are there
No.
any plans to?
You should ask a longer question. Yes, in the sense that we are at the moment very brainstorming about what we call LOFA 2.0, so an upgrade. And what we also find is that calibrating LBA data is really hard. And what would really help is simultaneously observing an HBA and LBA. And the basic problem there is we need to have electronics in place. And 7, 8 years ago, I mean, the electronics for a single LOFA station was 100K euros or dollars. And if you want to do that simultaneously, yeah, you need to spend 200, which is a lot of money if you have 50 stations. I think at the moment the price of this electronics is going down, and this is something we really like to be doing. So it's, if you think about it, is that it's all a computing problem. Because, I mean, the dipoles, they get information from the entire sky. So if you really sample the dipoles and keep all the data, you should in principle be able to make a map of 100 microjensky's all sky. And the only problem we can't do that is that the computers are just would start smoking, but it's a computing problem. So all the steps, we go for phased array with one beam. The only real reason to do this is simply because you reduce the amount of data. Yeah.
You mentioned that you were doing cosmic ray physics
Yeah.
with these as well.
Yeah.
Sorry, do you know about the detection event rate that you can achieve those for individual cosmic rays, and what sort of angular resolution do you have? Some sort of reconstruction pointing back to cosmic ray source.
Listening to the people that do this, because I'm not doing it, I think you get many a day for energies of, in the core, for example, of energies of 10 to the 18, 18.5, 19. And think of detection of 20, 30, 40 a day.
Okay.
Yeah, and so the pointing accuracy is, I think, well within a degree.
Are they have they published a paper on this yet, or?
Oh yeah, there are many papers on this. I mean, at least 10 or 20. And the last one was in Nature, by Buiting it all showed up, where with they feel with they can really constrain aspects of the nature of the cosmic ray coming in, the mass, or whether it's an iron or higher or lower. Yeah.
You went by the sausage, showing us the basic pieces. Can
Yeah.
you go back to your sausage spectral index map? There's all kinds of stuff there.
Yep.
Is there at least even speculation of what some of the other pieces, bits and pieces are?
Up. Let me Okay, let me do it this way for you. So this is the northern part, but if you look at the southern part, it's so I think what you're seeing there is multiple shocks from substructure in the cluster that is creating this, and that makes it fairly complicated. And probably a very likely combination effect is that if you look at the underlying medium, there will be still leftover pockets from previous AGN.
What about the other piece that's sort of off to the side of the north? This other guy will be sitting out there. This guy kind of got a little bit lost.
I think the same thing there, where you basically have some kind of substructure within the cluster that you don't really see in the X-rays because it's too subtle. Yeah, and of course those are the angle tails that you really, yeah.
So if I was going to count the wide angle the tails, there seems to be a preponderance of them going north.
Yep.
The rest, if you go down, there's one, but there's some.
Yeah, so one, but there's more going north and going south.
Yeah.
So for
Yeah.
people with mass merger,
See that one's going inside.
yeah.
Yeah.
But even this guy,
Yeah.
was going.
No, that's one of the things I haven't talked about is that, which is part of Andra's thesis, we've done very deep H-alpha imaging for those clusters. And so what we wanted to do is see whether those shocks have a real impact on the properties of the galaxies. Yeah, where the idea is that such a shock might either strip the galaxy of the gas, or it might induce star formation within such a galaxy. And I find the results very puzzling, because we have those two clusters, with the toothbrush and the sausage, and one of them has really is overabundant in H-alpha emitters, and the other one isn't at all. And we don't know, we just don't understand why. That's why I skipped it. Yeah, I think.
You showed the image of M82. And
Yeah.
what you saw were supernova remnants.
Correct. Yeah.
What were the scales that you were probing there? Like, how do they compare to what you see in optical X-ray?
Let's go there. Arcseconds, yeah. No. So, yeah. Well, you see here the 1 arcsecond is 1 kiloparsec. So, and I think the resolution here is of the order of half an arcsecond, maybe 3.4. Yeah. Yeah, it's pretty amazing we can do this.
So if there are no more questions, thank you for giving us a talk on everything from cosmic
Yep.
rays to supernovae to clusters. Pretty impressive. Thank you
Okay,
very much.
thanks.
During the normal observing
Can do it because there's basically a triggering mechanism that